Hello to everyone. This lesson is about antiderivatives, and this is really the reverse process of a derivative. So we're actually going to take the process and go backwards. So a lot of this lesson is going to be really just notation, different ways of writing things. And so number one here, I want to start off with what I think would be a question that we can answer right off the bat. So this question here is saying, let's find a function. We're going to call it capital F of x. So find a function whose derivative is this function here, little f of x, which we write as 4x cubed. So this example is meant to be fairly straightforward, like we could almost guess by looking at it. So we think this function is the derivative of something, and that something would be x to the fourth. So typically we could write something like this. So capital F of x is equal to x to the fourth. The interesting thing about this, though, is that this would not be the only answer. Like, we could tell that if we differentiate this, we will get this function, 4x cubed, so that is without a doubt. But there are many other examples. So x to the fourth plus 7 would also be suitable. In fact, you could take x to the fourth minus 3. And so the list here is really endless. So what we're really saying here is that the capital F is not a single function, it's actually a collection of functions. So we get an entire family of antiderivatives that are associated here. So what we will normally do is we will express this answer in a nice compact way. We'll write x to the fourth plus c, where c is some mathematical constant. So really the best answer to give here, find the capital F, the antiderivative, any function of this form, x to the fourth plus c. So I want to talk briefly here about the notation, because this will be the standard way that we have of writing things. So in our previous example, I'll just echo this up here. So the little f was 4x cubed, and this is the function that was provided, and then this is what was sought after, the capital F of x. So a definite relationship that we can see here right off the bat is if capital F is an antiderivative, then that means if you find its derivative, you're going to get the little f. So this is the standard way that we understand this. So this is a little bit cumbersome to write all of this, so we're going to come up with a nice, compact mathematical way of expressing this. And so we're going to see this a lot in the rest of Calculus 1 and also in Calculus 2. So this is going to be the standard way of expressing the fact that capital F is an antiderivative of little f. So you can see this is the function that was given to us in the problem, the 4x cubed, and this is our way of saying that the answer we get is not a single answer, right? But it's a collection of answers, the capital F function plus the constant. So this is our new notation here for an antiderivative. So this is indicating to us that we need to take the process in reverse. So we need to look at this function and find its antiderivative, right? Actually reverse the process. So that's the standard notation. This is anti-differentiation, or we can call it integration. So we're going to be using this notation quite a bit. So something we don't talk about a lot at this point is we have the little f and the capital F, but we're revisiting this little thing from a previous section. So this is the differential of x. For now, we can just say this is telling us that the variable that we're working with is the x variable, but there are many, many times in mathematics where the dx as a differential interacts with the function. So it's very, very important to understand that really you're working with two things on the left-hand side. So just to provide some context here so that this makes sense, in our last example, we would have written this down. So this is the way of expressing it in the new notation. So I want to do this just so everyone can be convinced that this makes sense. So this is our way of saying x to the fourth, right, is the antiderivative of 4x cubed, and we're using this notation here. And so this is our integral symbol that indicates we're going to integrate the function or find the antiderivative. So this is what was provided to us, the 4x cubed, and what we ended up coming up with was this answer, right, x to the fourth plus c. So this will be the standard way of expressing that. Alright, so I want to share with you just a couple of quick examples so we can become fluent in this notation. Some pretty easy ones here. You should be familiar with these. Alright, so when we see something like this, really the question becomes, what function out there has a derivative of 1 over x? And this is something we encountered a couple of chapters ago. So this here would be the natural log function, and then plus the constant. So all this is telling us is that if we differentiate the natural log plus any constant, we end up getting back 1 over x. So we can take a look at another simple one here. And again, this is meant to be simple, right? It's a matter of recognition. So we see an example like this, and we're looking at that and saying what function out there has a derivative that's cosine? That would be the sine function. So we have the sine of x and then plus the c. So we get that family of antiderivatives. Alright, so the big thing I want to talk about now is that there are some basic integration rules because we are accustomed to differentiating functions, and we have a long list of rules there. So we should also talk about one integration rule in particular, a very important one. So I'm going to show you both side by side. This is the old rule from derivatives, right? The basic power rule. And I want to show you the new rule, the integration rule, right next door, because you can literally see that these are the opposite process. And then we'll take a look at an example to see if we can see how it looks in action. So if you were to describe the power rule in words, literally we take the power out in front, we leave the x alone, and we drop the power by 1. So we're actually multiplying by the power and then dropping the power. Now if you look what happens when you reverse the process, when you integrate a power function, you can tell that instead of dropping the power by 1, you're actually going to increase it by 1. And this should make sense because we're going in reverse. And then instead of multiplying by the power, we're dividing by that same power, the n plus 1. So this is the antiderivative formula. This is the old derivative formula. So why don't we take a look at an example of this, just to see what it looks like. So remember here, this stuff is not terribly hard, but you do have to be careful with the algebra. So I'll push this right here so we can follow it. So this problem is only different in the sense that the differential, or the variable that we're working with, is now t. But if we look at this carefully, this is just a power function in which we can apply the power rule for integration. So if we look at this problem and express it as a power, this would be t to the 1/2 power dt. So as soon as we have this expressed as x to the n or t to the n, then we're all set. So all we're going to do is to increase the power by 1 and then divide by that same number. So we're going to add 1 to 1/2. So this will look like t to the 3/2 and then divided by the same number, 3/2 plus c. So what we have here is the antiderivative. And so division by 3/2 is the same as multiplying by 2/3. And that's it. So that problem is history. It's finished. So this is our collection of antiderivatives, and a quick check here is that if you differentiate this answer, what should happen, right, if everything's fine, is that you're going to get this function back. So finding the derivative of 2/3 t to the 3/2, you'll notice that if you differentiate that function, the 3/2 and the 2/3 will cancel out, and this is going to drop by 1. So what you're going to get when you differentiate this, the constant disappears. And so upon finding the derivative, this is one way you can always check. So when you differentiate this answer, you will always recover the original problem. Because what we're saying is the antiderivative and the differentiation process are really circular. Right? One of the processes is going to invert or reverse the other. Alright, so I want to close with a couple of slightly more advanced problems, but if we stop and think carefully about these, I think that they're pretty manageable. So I'm going to put a new problem up here, and we can talk about it. So here we go. This problem is saying, really, we're going to work out this problem here on the bottom, but it's asking us, let's see if we can go backwards with the secant squared of 2x, but it tells us here that we should think about this function first. We should think about comparing it with that example. So we might recall right away that the antiderivative of secant squared is going to be the tangent function, and that is because if we take the tangent function and we find the derivative, we get the secant squared. Right? So that means the answer to the top problem would be the tangent of x plus c. So we would get a collection of antiderivatives. So it's very natural here to say that the answer to this one is probably going to be the tangent of 2x. So that is something that we should initially attempt. So the tangent of 2x, when we find the derivative, right, from the chain rule, this will be the secant squared of 2x. And then the derivative of 2x is going to give us 2. So you might notice right away that there's a little problem with this one, because this one is asking us to go backwards with secant squared of 2x, not with secant squared of 2x times 2. So what we can do here is to slightly modify. We can really take the 2 and really move it to the other side of this equation, and that should solve the problem. So what we're going to do is to upgrade the step here. We're going to take one more step, and I'm going to recommend trying 1/2 tangent of 2x. So we're going to differentiate this. So if we differentiate this function, the 1/2 is a constant multiple. And then tangent 2x, we already know that's going to give us the secant squared of 2x, right? And then times the 2. And so what you'll notice here that happens when we do this is that the 1/2 and the 2 pair up. And so these will disappear, and what we end up with is exactly what we want, right? So we have found a function whose derivative is exactly secant squared of 2x, and that answer would be 1/2 tangent of 2x. So then to answer this bottom question, we could just express it this way. So this is what I want you guys to get used to. So we're going to integrate the secant squared of 2x dx, right? And the answer to this would actually be this function here plus c. So it would be 1/2 tan 2x and plus a constant. So notice the way you get that is by a little bit of trial and error. So you look at the basic function, a slight little modification, and if it doesn't work out perfectly, you can just adjust the problem. Alright, so we're almost done. I'd like to do this just for one more, and that'll be it, right? This is just to kind of get warm with the idea of the notation, right? The differential of x, the integration symbol, and then the process of just going backwards. So I'll give you a moment here. If you think about this one again is a very recognizable one. So this is one that we talked about when we discussed inverse trig functions. So this is the arctangent function. So we could write it this way. So the derivative of the arctangent function is precisely what we see here. So we derive this via triangle trigonometry, right, and things of that sort. So what we're trying to do in this problem is not to get 1 over 1 plus x squared, because what would solve this top problem would be the arctangent of x plus c. So we want to get this extra little 9 in there. So you have to think a little bit about composite functions, right? So we have x squared, and here, if we look at the second part, this would be the equivalent to 3x raised to the second power. So what I would recommend here is to do the arctangent of 3x. So we'll try that and see where it takes us. So arctan of 3x. I'm going to find the derivative. So remember here the basic rule for this one takes this form, 1 over 1 plus u squared. So this is a while ago that we talked about this, times du dx. So this is the chain rule form for the arctangent of u. So in this problem, the u is 3x. So what we're going to end up with here is 1 over 1 plus 3x to the second power. And then we have to take the derivative, right, du dx. So the derivative of 3x is going to be 3. So if we look carefully what's in red here, this is very nearly identical to this. It's very, very close. This would give us 1 over 1 plus 9x squared, right? So we have the proper form, but we have the extra 3. So this is more or less the same thing that happened with the previous problem, right? Having the problem with the 2. So this is something I think we can reconcile pretty quickly. I'll take this down here. So I'm going to take one more natural step here, and so if we want to discard the 3 here, we should try 1/3 arctan of 3x. So here goes. So 1/3 the arctangent of 3x. Alright, so when we differentiate this, the 1/3 is going to show up as a constant multiple. So 1/3, and then we're going to get this thing right here. So 1 over 1 plus, and I'm going to write this as 9x squared. And then we get 3 from the chain rule, right? That comes out. And so notice a very similar cancellation here, the 1/3 and the 3. That's going to leave us exactly with what we're looking for here. So this is telling us if you want this as the derivative of some function, you would have to use this function here, that 1/3 arctan of 3x. So let's write that down so we can see that. So we would express it this way. We could say the integral of 1 over 1 plus 9x squared dx. Okay, and what that's going to be, the answer is right here. So this will be 1/3 the arctan 3x. That would be plus c. And just like the previous problem, a little bit of thinking that has to go into it, and a little bit of trial and error as well. But this would be our final answer. And notice it really does come from, if you think back, it comes from knowing the basic form and then seeing that this is a generalized version of what we have there. And so that's how we do many of these problems.